many practical problems, the surface or volume of a body may be subjected to distributed loading. Loading may be a result of wind, water, weight of the material supported by the body, or of the body itself. Let's consider a beam supporting a distributed load. Shown in Figure A is a beam with the load curve plotted over its length. Each unit length of the beam supports a load W, which may be expressed in Newton per meter or pound per foot. The area of a typical narrow strip of width delta x under the load curve is W delta x and is equal to delta F, which has units of force. We can consider each narrow strip under the load curve as representing a series of parallel loads. The resultant and location of the resultant may be found by the methods of integral calculus and resultant of parallel forces. The resultant concentrated load is equal to the total area under the load curve. It can be said, without proof, that the line of action of the resultant passes through the geometric center or centroid of that area. The resultant of a distributed load can be used to find external reactions for the beam, but cannot be used to find internal reactions or deflections. The types of distributed loads are the uniform load and the triangular load. The first type is a uniform load, which may be represented by a rectangle, the height of which represents the load per unit of length, expressed in pound per foot or newtons per meter. The length of the rectangle is the distance over which the load acts, expressed in feet or meters. The resultant of a uniformly distributed load is equal in magnitude to the area of that rectangle, which is R equals W times L. It acts at the geometric center in the middle of the rectangle and at a distance L over 2 from either end. The second type is the triangular load. A triangular load varies uniformly from 0 on one end to a maximum on the other end. The height represents the load per unit of length, and the length is the distance over which the load acts. The resultant of a triangular load is equal in magnitude to the area of the triangle, which is R equals WL divided by 2. It acts at the geometric center of the triangle at a distance 2/3 of L from the pointed end of the triangle, and a distance of L over 3 from the flat end of the triangle as shown in the figure. Let's look at this example. It asks us to determine the resultant of the distributed load shown in the figure. If you look at the figure, we can divide the distributed load shown into one uniform load and a triangular load on top. The uniform load has an area of WL equals 5 kilonewton meters times 4.5 meters equals 22.5 kilonewtons, and acting at a distance of L2 equals 4.5 meters times 2 equals 2.25 meters from A. The triangular load has an area of WL over 2 equals 14 kilonewton meters times 4.5 meters divided by 2 equals 31.5 kilonewtons, and acts at a distance of 2L divided by 3 equals 2 times 4.5 meters divided by 3, which equals 3.0 meters from A. Two of those resultants are shown here in this figure. To find the total resultant, the equation is the summation of the two resultants, 22.5 plus 31.5, equals 54 kilonewtons. If we want to find the location of the final resultant, which is the R bar, we use our previous equation. The summation of moment A, which is 22.5 times 2.25 plus 31.5 times 3, which equals the total moment of 145.1 kilonewtons per meter, which yields R bar. R bar equals 145.1 kilonewtons per meter divided by 54 kilonewtons, which equals 2.69 meters as the location of the final resultant.